Angela? Oh, good Lord. Where are you? You're not in, like, the Waffle House or something, right? Like, I don't want to be teaching chemistry to all of Panera. Hi, Mackenzie. Awesome quest. Okay, everyone in there's heard me before, so not too weird. Not too weird. Ask away. I'm here. You got me for an hour or so. I gotta go back to grading lab reports, though. Got red with me. I just pulled some red off. Hi, Brandy. Hi, Onyx. You're going to have to move red if you want up here. And he's bigger than you. My dogs are vying for attention on the bed. Come on. Come here, Onyx. Come on. Come on. And suddenly there was dog. I'm in the dog's room because they're less likely to fuss at me. So. Here you go, girl, Onyx. What is this? What are you doing? She's like, scratching her neck. Alright, what do we got here? Oh, Diels-Alder reaction with multiple substituents. Okay. Yes. Oh, my dogs are cute. Crazy ones. I see you, Lauren. And then, okay, so Angela, let me get to those other questions first because they're easier. So Brandy, yes, if you have benzene chemistry where you're doing the nucleophilic substitution on a benzene ring, you're going to have the ability for it to hit at either side of the alkyne, the triple bond. So you could have a mixture of two products if you have multiple substituents on the ring. Okay. And then, okay, let's do a Diels-Alder. Let me pull up the right screen. The mechanism for a Diels-Alder is pretty easy, right? The hard part really is drawing the products and thinking about the type of stereochemistry you would get out of the products. So what you need to remember is that, and let me put this, actually let me double check to see if it's, is that too small to see? Tell me if those structures are too small. But I'm not, but I'm here. Did it stop streaming? I don't know what's going on. I had this problem last week too. Okay, let me make that bigger then. Let me know if that's better. I'm going to type this because it's telling me that the feed's not getting a good signal. so with a Diels-Alder reaction, remember how I said it's like two pieces of bread on a sandwich kind of like coming down on each other? You have to kind of remember that, and you need to remember what type of stereochemistry you're going to need for that. So if I have, let's say, this molecule here. Okay, good. So Angela, so let's say I have the molecule that I've drawn here, this diene, right? So if it's a diene, it can undergo a Diels-Alder reaction, right? A diene could undergo a Diels-Alder reaction as long as there's, you know, two conjugated double bonds essentially. So the thing is that the way, and I'm hoping you can see this bond that I'm highlighting, this one between the two carbons, the bond between carbons 2 and 3. So that one has free rotation, right? Because it's a sigma bond. And so basically what you kind of need to do is rotate this in your head so that it is in the type of conformation that can undergo a Diels-Alder reaction. Okay, so essentially all I'm doing is flipping this image around, just twisting it around that sigma bond so that those two alkenes are pointing in the same direction, okay? Do that, then you can't get a Diels-Alder reaction to happen at all. Okay, so that's an important point to note. Of course, I would never give you one on an exam and say, you know, psych, you can't do this one, but try it anyway. I mean, I would never intentionally do that. Okay, so first off, that's your first thing. All right, make your diene so it looks like it's pointing in the same direction. Then we're going to have your dienophile. So, excuse me, kind of the classical Diels-Alder is one that has some sort of aldehyde or a ketone or some sort of carboxylic acid or some sort of electron sink is what they call them in biology. Hi, Heath. We're talking about Diels-Alder reactions. So here, I'm going to take this, and I'm also going to move that at this point. Hi, Melissa. Man, like, the whole class is here tonight. But yes, I would love it if you're like, yes, I understand what you're talking about, Dr. Mann. So dienophile, make sure that they look like they're in a way where you can kind of anchor them in your mind to do the mechanism. Because if you can do that, you're going to have a much better time, a much easier time of figuring out your products, okay? So here, put on my plus sign, and let's do this chemistry. So the way I like to do it is I kind of like to number them. So I think I can do this thing. Hold on a second. Control C, Control V, make it a bit bigger, and swap over. There we go. Okay, so I can draw on that now. Okay. So the important thing here is that you kind of have some sort of anchor point so that you can see what you're doing. That's really like the trick with a Diels-Alder reaction. So for me, I'm going to notice that the carbon here is on the same side of like on one side with an OH group, and down on that other carbon comes off a CH2 and a CH3. So that's one thing I can do to kind of anchor my spot in my mind. The other thing is that I know these here are what are going to have to form the ring. Okay, so that's that pericyclic thing, and we can do the diene attacks the dienophile, we get that kind of deal, right? this mechanism before. It's that pericyclic mechanism, and that part's not really too hard. So the thing that you need to realize is that a pericyclic reaction will give you a cyclic product in a Diels-Alder reaction. Okay, so so if we already have, let me try and color code this. So this carbon here, I'm just going to go and name that 1, 2, 3, and 4, 5, 6, 7, and 8. Sometimes just numbering it really helps in being able to see what you're trying to do. Okay, so carbon 1 and carbon 6 need to form a bond together. Carbon 1, 2, 2, 3, 3, and 4 are all still going to be bound to each other, but carbon 4 and 5 need to form a bond, right? That's what those red arrows are showing. So I'm just going to draw a 6-membered ring, cyclohexane, right? Now, I need to remember that at this point here, we get a double bond forming. That's part of that reaction. And I also need to know that there's going to be 2 groups over here. Well, on a ring with an alkene, there's no difference in where those can point. Okay, if they were sp3 hybridized, you could get one going up and down. What? I didn't think it was that bad. I didn't ask you to draw it as a chair conformation. So let me know if that makes sense.